What I'd like to do is I'd like to compare a general uniform distribution model with a general exponential distribution model. I'd like to make a comparison there. So recall with a uniform distribution, we usually with a uniform distribution think about starting with the PDF because that's the simplest thing to think about. Because with a uniform distribution, the PDF is a constant function over some finite interval. And if we're talking about a survival random variable that can't be negative, we don't want to have any negative values with positive probabilities. And in fact, since technically, a newborn baby or appliance could die right away, we want to allow arbitrarily small positive values. We want to start at 0 and go up to some date. Maybe for a person, it would be 100 years. Maybe for an appliance, it would be 20 years. Actually, in the general literature, in textbooks, you'll find that the ending date, so to speak, or the drop dead date is typically called omega. Why? I guess like alpha and omega, beginning and the end. That's probably the reason. It's a little omega. And we're going to have a constant value over this finite interval. And to make the area 1, we better use 1 over omega for the height of this PDF. T is the variable. This is a PDF. F of t, again, as always, it's technically a piecewise function. It's 0 over here, 0 over here. It's 1 over omega when t is between 0 and omega. I'll just write that part of the formula. 1 over omega if t is between 0 and omega. Should I include the endpoints? Again, it's not a big deal if I do or don't, as always. So there's my PDF in a uniform distribution. Let's then find the CDF. This is a PDF, probability density function. CDF, cumulative distribution function, will be an antiderivative of this, making sure we start with a value of 0 at time 0. Its slope would be 1 over omega. And it would get up to a value of 1 once you reach omega. And be 1 thereafter. Again, technically it's 0 when t is less than omega. That would be the CDF, capital F of t. Now that we know about survival functions, we can now find the survival function easily from this. SF, in my handout labeled sigma of t, many actuaries labeled S of t. The most official actuarial notation for this is TP0, the 0 emphasizing that we're thinking about a newborn. Doesn't matter what notation you use, it's 1 minus the CDF. It's the complement of the CDF. So I have to imagine taking this graph and subtracting it from 1. When t is negative, I'm doing 1 minus 0 is 1. So the value is up at 1. When t is bigger than omega, I'm doing 1 minus 1 is 0. And when t is between 0 and omega, it's a linear decreasing function. Yeah, when t is between 0 and omega, the formula for the CDF is t over omega. If t is between 0 and omega. And therefore, for the survival function, the formula would be 1 minus t over omega if t is between 0 and omega, which could also be written if you get a common denominator as omega minus t over omega if t is between 0 and omega. My ultimate thing that I'm most interested in comparing this uniform distribution with an exponential distribution is going to be comparing their conditional survival functions. I haven't talked about that yet. But let's go ahead and compute the force of mortality anyway, to remind you about that. Force of mortality, FM. Whenever actuaries see FM, they think financial math, but here it's force of mortality. FM mu of t, not a mean, Yes, inconsistent notation. It's negative sigma prime of t over sigma of t. If I use the sigma notation, it would be negative s prime of t over s of t. If I use the s notation, it would be the negative derivative of this thing with respect to t over itself if I use that notation. What does that equal here when t is between 0 and omega? Take the negative of the derivative of this. The derivative of that is negative 1 over omega, right? That's the derivative of this right there. Over itself. Distribute that minus sign here into the top and also multiply the top and the bottom by omega. I'll get a positive 1 over omega minus t. If you do that. Once again, if t is between 0 and omega. That has a graph that looks like this, and that's the kind of graph that's got a vertical asymptote corresponding to the drop dead date of omega. Okay, sorry to be so blunt with drop dead, but it's quick to say. That appliance has got a built-in drop dead date. We talked last time about that you can interpret force of mortality as being proportional to conditional probabilities over small time intervals if you assume the appliance has made it to a certain age. Not going to go into more detail about that. You don't have to know that for the exam, but I'm just reminding you just for the future in case you're interested. But let's also compute now TPX. TPX, what is this? This is a survival function for a client, age X. Okay, I didn't use this notation in any of the handouts. It represents your probability, your conditional probability of living at least T more years if you assume you've made it to age X. I have mentioned this before, but I think a week ago I talked about this. It's the probability of living an additional T years. Actuaries write that like this. T sub X is greater than T given T being greater than X. What's T sub X? It's what I in the handout called T of X, where X was the client. It's T minus X. If you assume a person has made it to age X, T minus X then is how much longer they have to live. Okay, I'm 55 years old. For me, X is 55, or well, 55.5 almost. How much longer do I have to live? I have no idea. Maybe I'm going to live 30 more years. Make it to age 85.5, say. T for me would be 85.5. X is currently 55.5, so this difference would be 30. Okay? Because that's what that is, this is equivalent to the probability that, well, replace T sub X with T minus X and add X to both sides. It's equivalent to this, which as a conditional probability can be written as a ratio. I did this before. It's the probability that this event occurs and this event occurs. I'm using set build no notation in a non-precise way. Don't be bothered by that too much. Just trying to emphasize that these are events. I could use an intersection symbol here as well. But the intersection of these two events is just one of them. It's just that one. Why? Because this is a subset of that. Sub-event, you might say. If you know a person lives past T plus X, well, you know they live past age X. Therefore, you can rewrite the top just this way, and now I'll get rid of this curly braces. You can write it like that. Because this thing is a subset of this thing. Again, I'm not being precise with my self-builder notation. That's bad mathematically speaking, but just for the sake of simplicity. Just trying to emphasize these could be thought of as sets, but I'm not saying how. And I could use the intersection symbol, but that's a subset of that. If this occurs, then that occurs. Therefore, I can rewrite the top just like that. And that's the ratio of survival function values for a newborn. This is pre-subscript t plus x. Actually, it's more typically written x plus t p 0 over x p0 is the most typical way actuaries write it. If we're using our sigma notation, this would be sigma of x plus t over sigma of x. This was in the handout. So with this uniform model, what does this equal? Well, there's TP0, sigma of t. I got to use this formula right there. In what I just wrote in both the top and the bottom. I've got to use this formula. I think I'll use this form of it right there. So, but I'm going to use the TPX notation now. Replace t with x plus t, I'll get an omega minus x plus t over omega all over omega minus x over omega. Those omegas will cancel, leaving me with omega minus x minus t over omega minus x. Probably better to write this, to split this into two fractions, omega minus x over itself minus t over omega minus x, which simplifies to 1 minus t over omega minus x. I have actually talked about this a week ago, just reviewing it. And what does the graph of this look like? It looks like this. It's a straight line going from 1 down to 0 once I get to omega minus x. And what is that telling you? It's telling you for this uniform model, if you know an appliance is x years old, they have omega minus x years to live, and the distribution is still a uniform distribution. If we found the PDF for this, it would still be a horizontal line. First find the CDF, do 1 minus this, then take its derivative. You still get a horizontal line between 0 and omega minus x. Though the height of that horizontal line would be no longer 1 over omega, it would be 1 over omega minus x. When you think about this kind of thing, think about x is fixed and t is the variable. This is a t-axis here. But then what's interesting is to ask what happens as x changes. As x keeps getting bigger, this graph moves to the left further. The t-intercept moves to the left. Until you have an appliance that's almost omega years old, it's going to die very quickly. But the main point is that it's still a uniform model, but a different uniform model. Let's contrast this now with an exponential model. And something interesting is going to happen. That's why I'm doing this. This is pretty cool. And this is good for not only actuaries to know, but it's also good for everybody else. You want to be a data scientist, you want to be an engineer, you want to be just a general business person. What I'm about to show you is good stuff to know. What about an exponential distribution? Once again, let's start it by starting with the PDF. PDF for an exponential distribution. Well, how do we write it? At first, we wrote it as 1 over beta e to the negative t over beta, right? Earlier in chapter 4. Beta turned out to be the mean. Some people use a mu instead of a beta, but I don't want to use a mu because that's going to be our force of mortality, so I'm going to avoid that. Another way this can be written, which I think I mentioned at least once, is lambda e to the negative lambda t, where lambda is 1 over beta. And recall, this is worth remembering, exponential distributions are related to Poisson in chapter 3, a discrete distribution. Think about our typical example that we talked about, earthquakes. Maybe you're in an area of Southern California, like one of my daughters is right now, where there's lots of earthquakes. Now, okay, really big earthquakes are pretty rare, actually, but even for California. But small earthquakes occur all the time. How small is small? I don't want to get into details. Maybe your certain small earthquakes occurs once every month or something. Maybe you can barely even feel it though. So maybe if you're counting earthquakes during a year, and S is 1 year representing your measurement unit, and lambda back in chapter 3 is representing the average number of earthquakes in a year, 12 once a month. Lambda would be 12 in that context. How is that related to an exponential distribution? An exponential distribution is the amount of time until the next earthquake. 1 month, 1/12 of a year. If lambda's 12, beta is going to be 1/12. Lambda being 1 over beta is equivalent to beta being 1 over lambda. If lambda is 12, then beta will be 1/12. You're going to have to wait on average about 1 month for the next earthquake of that size. It's described in chapter 4 as the amount of time until the first earthquake. But there's been many earthquakes over the year. Maybe it'd be better to describe that in terms of the amount of time until the next earthquake. Is there a distinction? We can do survival analysis. Think about it with actuarial science if we want to try to understand what I just said there. So this is the PDF. I'm going to write it in terms of lambda. What's the CDF? And of course, the graph of the PDF looks like this. Looks like an exponential decay. This is for T positive here. There's no drop dead date, right? Because this goes out forever as with the t-axis as a horizontal asymptote, it never touches the t-axis, or it gets very, very close. The PDF actually has an intercept that's not equal to 1. It's equal to 1 over beta, which is the same as lambda. And if we're talking earthquakes and lambda's 12, that's going to be pretty high, actually. It's going to be up at 12. On a typical scale, I'd draw it more like that. What's the CDF? Capital F of T. It's an antiderivative of the PDF, but not just any antiderivative. It's one that's got to go through the origin and increase up toward 1. So it's not any old antiderivative. It's a particular one. Yeah, we could write it this way. I'll let you confirm that if you do that, you'll get this in the end. And you can check in your head, if you differentiate this function, you do get this function. All right, check, differentiate that. 1 differentiates to 0. Negative e to the negative lambda t differentiates to what I'm pointing at here with my left hand. Lambda e to the negative t, the negative signs cancel. Get an extra factor of lambda because of the chain rule. And the negative signs canceling. That ends up being the CDF. What's the survival function? SF. Call it sigma of t or S of t if you prefer. Or, okay, how about TP0? It's 1 minus the CDF. 1 minus this is going to be just e to the negative lambda t. Huh. When the PDF is an exponential decay, the survival function is also an exponential decay. Interesting. You wouldn't necessarily know that ahead of time. Though it's not the same exponential decay. It's got a different vertical intercept. This one has a vertical intercept at lambda. This one has a vertical intercept at 1, as all survival functions have to do. Not lambda like this one. Okay, we're going to come back to the survival function. Let's go ahead and again, for completeness, compute the force of mortality. Something interesting happens here. Mu of t is negative sigma prime of t divided by sigma of t. Negative, or okay, sigma prime is negative lambda e to the negative lambda t. That's the opposite of the PDF. We've seen that before. Divided by sigma of t. The negative signs cancel. The e to the negative lambda t's cancel. That's a constant function. The force of mortality in an exponential model is a constant function. That should seem unlikely to occur for lifetimes. Certainly not lifetimes of people. Because remember, the force of mortality, its value could be interpreted in terms of conditional probability. Essentially, what this is saying is if you got this newborn baby, maybe it's your baby just been born, you're wondering how long they're going to live. I don't encourage such thinking, but say to yourself, okay, if I assume this baby makes it to 100 years old, what's the chance that they die in the next day? I have to multiply the force of mortality by 1 over 365 if the units for time is years, as an approximation for that. But this force of mortality is constant. So effectively what it's saying is it doesn't matter how old you assume they make it to, the probability of dying in the next day is the same. That doesn't make any sense. Does this model apply in lifetimes? Probably not. Some people say it models lifetimes of light bulbs. Is that true? I don't really know. I've heard people say it. It seems really random, like when light bulbs burn out. I mean, this was much more the case with incandescent light bulbs, not with the light bulbs that have been on the market the last 10, 15 years. But before that point, these incandescent light bulbs, these old light bulbs we'd get, you'd have no idea how long it lasts. It might last just a few days. It might last a year or two. I don't know. Maybe it's more believable for light bulbs. Anyway, coming back to comparing TPX now, in this context, writing it as sigma of x plus t over sigma of x, what happens here? Something interesting happens. I'm going to use this formula here. Pointing out with my left hand there. I get e to the negative lambda in parentheses x plus t divided by e to the negative lambda x. And then, I'm really tempted to do this. Should I do this? It's certainly okay to do this because of properties of exponents. And look at this. Cancel, cancel. E to the negative lambda t, which is the same as TP0. For an exponential model, the survival function doesn't depend on the age. That's what I was just saying here with the force of mortality, essentially. This is not typical. This is very special for exponential models. They are exponential distributions are said to be forgetful. This is an official term. They are forgetful. They forget what age they are. They forget, if you think conditional probabilities equal ordinary probabilities. It's kind of like independence. It doesn't matter how many earthquakes has happened in the past or if an earthquake just happened or not. The amount of time you have to wait for the next earthquake doesn't think about the past. Now, does that really happen in real life? Well, I don't know. You'd have to get into geology and earthquake science to know for sure. But as a model, maybe it's reasonably accurate still. I don't know. They have this forgetfulness property. Very special. Okay. And if you graph the survival function, it'd be the same as the graph of the original survival function. It would look like this no matter what x is. That's also interesting to think in terms of graphical transformations, because this formula is a graphical transformation of the original graph of sigma of t. Sigma of x plus t, if x is positive, is a translation to the left. If I take this graph and translate it to the left by X units, what will I see? I'll see something like that. And then dividing by sigma of t, which is dividing by a number less than 1, is the same as multiplying this by a number bigger than 1, is going to stretch this up. And if I ignore this part, what this equality is ultimately saying, this is the same as sigma of t, is that the resulting graph that I get after leftward translation and an upward stretch is the same as the original graph. Yeah, that's very special. Doesn't happen with most functions. Okay. Actuaries need to know this. It's good for other people to know too.